Hi everybody, this is Dr. Bricker here with a review for Exam 3. So a few things about Exam 3. First of all, what's it over? What's it look like? And we'll have to answer all those questions. So it is going to be online. It's going to have 12 questions, just like the practice test. It covers Chapter 6, which is circular motion, and we just did a little bit from Chapter 3, also with circular motion. So make sure you look back at Chapter 3. The part with radial acceleration. So Chapter 6, Chapter 7, which was rotational motion, Chapter 8, so 8.1 through 8.3, it's called equilibrium, balancing forces and torques. So we didn't do anything with stretching or compressing materials in Chapter 8. We just focused on the first three sections of Chapter 8. And then we talked about Chapter 14, which is simple harmonic motion, mass on a spring. So take a look back at that. And most recently, Chapter 15/16, standing waves on a string. So we didn't do the entirety of 15/16 either. We focused on waves on a string. There's waves in tubes, standing waves in tubes, things like that. We didn't do that. We just did waves on a string. The homework that goes along with this test would be homework 7, 8, and 9. So make sure you look back through that. And homework 9 is actually due Wednesday by 4:59 p.m. So make sure you complete homework 9 before this test. Now, if I were to study for this test, I would go over the practice test. I would look back through the homework assignments that go along with the test. So basically, homework 7, 8, 9. Read through these chapters. It looks like there's a lot of material, but we didn't do the entirety of all of the chapters. Like, for example, Chapter 8, we only did the first three sections. Okay, if you don't have time to read all the chapters, at least look at the summaries at the end of the chapters. And then go back through the PowerPoints and the videos. You basically have a video either in class or me making a video going over the PowerPoints and homework for all of this material. So you've got a lot of resources at your disposal. Hopefully you've already started looking at that. So where are you going to actually find the test? Well, it's not in person. Remember, it's going to be online. Let me show you where that's going to be. Okay, so this is the Brightspace page here, and let me actually change it to look just like what it looks like for you. View as learner. Okay, doesn't change too much, but a little bit. Now, if you notice over here, on the side over here, Exam 3 availability ends at 7 p.m. So the exam will actually be available to you Wednesday from 5 to 7. Usually you only get an hour and 15. This you get 2 hours. Not that it's any longer, but I think maybe it's more cumbersome to show your work in this environment. I mean, in class you just write it down, you hand it in. Here you have the option of typing out your answer, or taking a picture of whatever you've done on paper and uploading it that way. So more about that in just a minute. It is still multiple choice, and I'll show you that in just a few minutes. But you have to show your work, just like before. Okay, so it's an online test. Maybe you've taken other online tests before, and it's completely multiple choice. It grades it immediately for you. Mine is basically kind of like a short answer test, but you have to show your work. And I'll go through the practice test, a couple of them like that, just so you see what it looks like. Okay, so make sure that you have set your computer on Central Time. It's available 5 p.m. Central Time Wednesday until 7 p.m. Central Time. So, take that into account. Make sure that you're on the right time zone. I think to check that, you would just click the little gear thing up here and make sure your time zone is correct. Regardless, it doesn't matter. It's available from those times, Central Time, 5 to 7, our usual time. Okay, so when you click here now, nothing will happen. It'll just tell you when it's available. It starts the 2nd, that's Wednesday at 5, ends at 7. Okay, so when you click on it, it would go through a few different things. So let me show you for example, what a test might look like. Okay, so I'm just showing you, this is an example of what it might look like. So once you click on it after 5 p.m., it'll look something like this. And it says once you get started, you have 2 hours to complete the quiz. It's called quiz. For some reason, Brightspace if it's a quiz or a test, they automatically call it quiz. I mean, the title of it is called Exam 3, but Brightspace refers to it as Start Quiz. So don't be thrown off by that. It's still going to be Exam 3. As you can see, it'll say Exam 3 up here. I'm just doing Exam 3 practice. You don't have access to this. You have the actual practice exam in the practice exam folder. I only made this pretend one so that you can see what it's going to look like for you, and there's no surprises. Okay, so it will have some instructions here. Okay. All restrictions on the availability have been bypassed for this preview. That's because I'm looking at it. Before you start the quiz, and again it says quiz, but it's really Exam 3, you'll have opportunity to return to questions you may have missed or not answered. You can submit your quiz responses at any time. Okay, so it's not the kind of quiz you can start it, come back next day and finish it or anything like that. It's only available to you from 5 to 7 p.m. Okay, so let me do start quiz here, just so you see what it looks like. Good, and the practice test has 12 questions. The actual test has 12 questions. So page 1, problem 1 and 2. Page 2, problem 3 and 4. You can bounce around. Say you don't like that one. You want to see what this one is. Okay, this one looks better. You can start answering it. Okay. Good, and I'm just in the preview. Don't hit submit quiz until you're completely done with it. Okay, and again, if you're working on it over 2 hours, it'll automatically stop it for you and save whatever work you've done. Okay, very good. So you see what it looks like, and I'll answer it in this format so you can see how you can submit some answers. Okay, so if you have the Practice Exam 3 I've given you, this is actually the first one on Practice Exam 3. Brightspace just randomizes the order of the questions, so although it says question 6 here, this is actually the first one that you'll be working on if you're going over the practice test. So find the first 3 harmonics of a string of linear mass density 2 grams per meter and length 0.6 meters when the tension is 50 newtons. And then here are the answers. So whatever the answer turns out to be, you'll have to type it here, but then, show some work. Now, it can be kind of cumbersome to do this, on a computer screen. I realize that. So there's a few things. I mean, we could try to do it on a computer screen. So maybe I will actually do that for this one so we can kind of see what it looks like. If you click this show all components here, you have a lot more to work with. Now, you could do it on a piece of paper, save it on the, the way you do it on a piece of paper, take a picture of it with your camera, maybe email it to yourself, save it on the desktop of your computer, and then you can upload it here where it says insert image. I'm just going to see how this actually works out, just try to type out the answer here. So let's see. I know that the speed is equal to the frequency times the wavelength, and there's a lot of different things you can use here. This graphical equation button might be helpful. There's a few other things you can take a look at down here. Let's see, insert symbol. You could use this if you wanted to do like frequency times wavelength. Let me just try frequency times wavelength. So the wavelength symbol is lambda. Let's see if I can find it here. And you don't have to make this as nice as I make it. I'm just showing you all the different options that you have. Okay, lambda should be somewhere around here. See, this takes a little bit more time. That's why I given you 2 hours instead of just the usual one. Lambda. And then my screen's a little bit small there, but there's the insert button. So frequency times wavelength. I also know that it's equal to the square root of the tension divided by the mass per length. So if you want, you could do this and then hit math equation. Let's see. I'm hitting this generate preview button. Okay, actually now remember, you have to hit this little toggle graphical button here. And then you can type it in any way you want to. So what I was going to try to do is tension, the square root of the tension divided by the mass per length. So there's the square root tension. So we were calling it force of tension divided by the mass per length. And let's see, that would be mu. Insert. Okay. Now I also know that the wavelength is 2L divided by m, so I can also do that. Equation editor. Hit this thing, and then the wavelength, that's lambda, equal to, and then 2L divided by the mass divided by m, and m is the mode. So I could insert that. Okay, so you can see that this is kind of taking a little bit of time to actually do this, but anyway, this is a good little refresher here. The wave speed's frequency times wavelength. The speed is also equal to the tension divided by the mass per length, and then the wavelength is 2L divided by m. Okay, so what we're given here is find the first three harmonics. Okay, if we just find the first harmonic, the second harmonic is twice the first, the third is twice the first. Okay, so we've got 2 grams per meter. That's 2 times 10 to the minus third kilograms per meter. And then here's the length. And we know the tension. Okay, so we know a lot of stuff. We want to then figure out the frequency. Okay, so let's take a look at this then. So if I look at this, frequency times wavelength is the square root of the tension divided by mass per length. I can plug this whole part in for the wavelength. So when I do that, I would have the frequency times, so frequency times the wavelength, but the wavelength is 2L divided by m. Maybe I'll do this again. Gotta click that. Okay, 2L divided by m. And then that's equal to, whoops, the square root of the tension, so force, there's a subscript, tension, divided by the mass per length. And I think it's over here maybe, yep. So unless you do this a lot, it's hard to even remember where all these things are, but I'm doing pretty good, I think. Okay, so frequency times 2L over m is the tension divided by the mass per length. And I'm trying to figure out the frequency. So then what I get is, I'll just put it over here. The frequency is going to be m divided by 2L times the thing in the square root part. So then the frequency is equal to, I'll do this again, m over 2L m over 2L, and then times square root of force of tension divided by mu. Okay, and then you could put the actual numbers in here, and you got to scroll down a little bit. So the fundamental frequency, that's when m is equal to 1, so I can use that. So I would have 1 over 2L, so this would be 1 over 2L. Okay, 2L. This is 1 over 2L, whoops. And then I still have the square root of the tension divided by the mass per length. Okay, so let me actually add that. F subscript T divided by mu. Insert. Okay, and then you have to put the actual numbers in here. So I would have 1 divided by the length. I give you the length in the problem. That's all the way back up here. So the length is 0.6, so 2L would be 1.2. So 1 divided by 1.2, and then we have the square root of the tension, which is 50 newtons, divided by 2 times 10 to the minus third. Make sure that you always put this into kilograms per meter. So I'm going to leave it at that without putting the numbers in. So I could already see that trying to actually type out the answer this way takes a lot of work. Trying to figure out the symbols, things like that. We're used to using a piece of paper, so I guess I would almost recommend using a piece of paper and going that way. Write it out on a piece of paper, take a picture of it, email it to yourself on your computer, or maybe you're doing the test on your phone already, I don't know. But if you can take a picture of it somehow, and then you could hit this button and then add a picture that way. So wherever you saved it, probably on your desktop, you could just hit my computer, and then when you do upload, you can look wherever you want to try to find it. Okay, and then you just hit add, and then they'll ask you something, and we'll go through one like this. Save it as a background decoration, and you just put yes for that one. But we'll do one like that so you see what that one looks like as well. Okay, so this is actually kind of a nice review of standing waves. This is really everything that we need to know for this. Okay, so put the numbers in, make sure you put mu as kilograms per meter, and see what you can come up with. Okay, let's take a look at another one. Okay, so this was actually the second one on the test that you have, the PDF version. An athlete holds a shot put in his hand, 7.5 kilogram, with his lower arm horizontal as shown in the figure. Okay, so here's the picture, here's the pivot point. His lower arm has a mass of 2.8 kilograms, and its center of gravity is 12 centimeters from the pivot point. So the arm on its own, the lower part of his arm, has a mass of 2.8. So if you have your arm in this position, the arm itself is trying to rotate clockwise. This shot put is also trying to make it rotate clockwise. What stops that from happening? It's this muscle here, this extensor muscle. And the extensor muscle is 2.5 centimeters from the pivot point. Okay, so extensor muscle trying to make it rotate counterclockwise. The weight of the arm itself and the weight of the shot put trying to make it rotate clockwise. But those are balanced. It's not going anywhere. So we want to know, how much is this force? Okay, let's take a look at that. I'm going to do this on a piece of paper, actually, and then show you how you can upload the image. Okay, so here's kind of a little bit of a sketch of it, not drawing the scale. So here's where they're telling us the center of mass of the arm is, 12 centimeters from the pivot point. The shot put is 0.3 meters over to where it's located. And again, not drawing the scale. Here's the distance from the pivot point over to where the muscle is acting. So all the torques are balanced. So the torque from the arm, from really the weight of the arm, and the torque from the weight of the shot put, making it go clockwise, balanced by the torque from the muscle, making it go the other direction. Okay, so if I'm going to balance torques, I could do something like this. Torque from the muscle, making it go one direction, is equal to the torque from the arm plus the torque from the shot put. Now the torque from the muscle, it's the force and then the perpendicular distance, which is just called r sub m here. That's going to be equal to the torque from the arm. So torque is force and then perpendicular distance. So the force, it's the weight of the arm, not just the mass of the arm, the weight of the arm. And then this distance is, I believe, 0.12 meters plus mass of the shot put times g. That's the weight of the shot put. And then the distance to where that's acting, the perpendicular distance, 0.3 meters. And then the only thing that you don't know in this problem is what you're looking for, the force from the muscle. Let me clean this picture up a little bit. So let's see here. I'm not going to put the numbers in, so I'm actually going to erase this just so it looks a little bit cleaner. Okay. Okay, I'm not sure what that was from. That's why I wanted to get rid of it. I wasn't sure what that actually was even. Okay, so that's most of the work here. Now you just have to put the numbers in. It's balancing the forces and the torques. Okay, so make sure you have a picture. I mean, I erased what I wrote down, but maybe I should have probably left that there. What the mass of the arm is, what the mass of the shot put is, and then you'll have another step or so, dealing with the, actually doing the algebra to solve for the force from the muscle. So just one more step to go. And so you did it on a piece of paper. You got the answer. Then you could list one of the answers. What I can actually do is just take a picture of my screen, however you want to do it. I'm ready. I'm doing this on my touch screen. You can probably do it on a piece of paper and take a picture of it. I probably should have done that. It would have probably worked out a little bit easier. But for you to be able to see it, it's easier for me to do it on the computer screen. So what I can do then is take a picture of it. I just want you to see what the final version looks like. So I'm going to take a picture of it with my phone, and again, do it on a piece of paper. It probably would be easier, or maybe if you have a touch screen, you can do it that way. However you can come up with to do this. Okay, and then I'm going to email it to myself. Okay, so I took a screenshot. I took a picture of it with my phone, emailed it to myself, downloaded it on the desktop, and now I'm going to see if I can insert it here. So I hit this. Let me show you what I did. I hit this picture-looking thing, my computer, upload, and I saved it on the desktop. So I'm going to click that. Okay, so again, I hit upload image. I looked on my desktop, found it, and you can see that it's being ready to be uploaded here. Storing course files, I'm just going to leave this as the default. I'm not sure what happens if I do it the other way. Probably it would be fine. I'm going to do add, and then this image is decorative. That's fine with me. I'm just going to do this. I'm not sure what the difference is here, but this is the way I found that it works out the easiest. Okay, and there's my picture of my work. Okay, and again, I did not put the numbers in. You'll probably want to do that. This way you can get some partial credit. And I would have whatever I got too. Make sure that if it's not in the picture, like if you did choice C or whatever, make sure that you actually do. I'm not saying it's C. I can't remember what it was, but clearly list what choice you're picking, and then have your work down here. Okay. Good. So again, the first couple of problems, I just wanted to let you see what it's going to look like. There's 12 of them. They're each worth 8.5 points. Okay, so let's go through the other 10 problems then. Okay, I'm not going to do them all online like this just to save a little bit of time. Okay, let's take a look at them. Okay, so back to the actual test then. Third one, in simple harmonic motion. Okay, think that's chapter 14. Hopefully you got a little simple harmonic motion area built for you. When is the speed the greatest? There could be more than one correct choice. So the class video we built a nice little table. But when is the speed the greatest? Well, the speed is the greatest, so we'll do this before we even answer it. The speed is the greatest when you pass through equilibrium. So at the endpoints, when you're at when x is equal to plus or minus a, that's where the speed is actually equal to 0. It's when x is equal to 0, when you're passing through the equilibrium point, that's when the speed is a maximum. And that's when all of the energy is kinetic energy. So let's see which one matches up with that. When is the speed the greatest? When the displacement is a maximum, so it's definitely not A. That's where the speed's actually 0. When the potential energy is a maximum, this is where the potential energy is a maximum, when you're at the endpoints. So that's not true. This is actually where the potential energy is 0. That's where the kinetic energy is a max. At equilibrium. So it's not this one. When the magnitude of the acceleration is a minimum. Okay, so the acceleration at the equilibrium point is actually 0. So that's one can't be true either. Okay, when the magnitude of the acceleration is a maximum. Okay, when the potential energy is 0. Good, so it's going to be this one, when the potential energy is 0, right? The potential energy is 0 through equilibrium. So let's go back here and carefully read C. I didn't address C completely yet because I'm thinking about when the magnitude of the acceleration is a minimum. Okay, so let's think about that. Here, at this position, the acceleration is either a minimum or a maximum, the magnitude of it. When it's all the way stretched out, it's a minimum. When it's all the way compressed, it's a maximum. But they're saying when is the magnitude of the acceleration is a minimum. So this would also go along with that, right? That's where the, again, it's all the way stretched. This is when the acceleration is a minimum. This is when x is equal to a. And then when x is equal to minus a, big A here, by the way, is the amplitude. This is where the acceleration is a maximum. So in a way, this choice C is actually, you can make an argument for this. When the magnitude is a minimum, well, the magnitude of 0 is 0. Isn't that less than taking the absolute value of this? And you could, so I would say that C, you could actually argue either way that one, maybe that's not true, maybe it's true. Based on the way that it's written, though, I think they're saying the magnitude is a minimum, but really 0 is less than the magnitude of this. On the actual test, there's just going to be one correct answer. When you get into these, there could be more than one correct answers, then you start second guessing yourself. Okay, so there'll be a similar one on the actual test, but there's just going to be one correct answer. Okay, so as far as explain goes, I mean, this little chart really explains it. You know, this chart here weeds out all the incorrect answers. Let's go back to the first couple of questions we did first of all. I just want to give you some more hints on that. So we did this one. This was balancing torques. Now on the actual test, there's not going to be an arm like this. Go back over the homework, and there's a problem or two where you have something like this that's being balanced actually. And then maybe you have this actually has a mass, and maybe there's a sign hanging here. So go back and look at those kind of problems. So in this problem, the weight of this beam itself, I'll just put weight of beam, weight of sign, these would both make it rotate clockwise, but you have some tension here, and then a Ty and a Tx. It's the y part of the tension that actually would balance the torques about this pivot point. So this is a good place to start. Look at this arm problem, but then go back and look at some examples on the homework and through the chapter about a picture like this with some kind of beam that has weight, maybe a sign hanging from it. Hopefully that rings a bell to you. And then you'll see something similar to this problem as well. Again, we use that the frequency times the wavelength is the tension divided by the mass per length, and then don't forget that the wavelength here is 2L divided by the mode. Okay, so man, it's a lot quicker to write on a screen than it is to try to type this stuff out. So I showed you how to enter the questions actually typing it out like that. It seems to take a while. It seems like it might be easier to do the work on a piece of paper, take a picture of it, send it to yourself, download it on your desktop or wherever you like to save it, and then upload it that way. It seems like that might be quicker. Good. I wanted to experience it myself and see which way is faster, and I know this way is going to be a lot faster. I mean, it took me 5 minutes, it seemed like, to type out this, which I just did in a second. Okay. I guess the only thing else, that's the speed. And then when you put it all together, you get the frequency 2L over m is the tension divided by the mass per length. Okay, so you'll definitely see a problem like this. This one I ask you for the frequency. Maybe on the test I give you the frequency and ask you for something else, the tension or whatever it turns out to be. And again, this term is the tension. Okay, good. I just wanted to go back to those and say a few things about them. All right, on to the fourth one. The total mechanical energy in a simple harmonic oscillator is. Okay, now the mechanical energy is made up of kinetic energy plus spring potential energy. So when all the energy is kinetic, it's equal to the maximum kinetic energy. This would be when x is equal to 0. And it's also equal to the maximum spring potential energy. That occurs at the endpoints, plus or minus a. Let's see how we can answer this one. A non-zero constant, okay, it's constant, it doesn't change. As long as there's no friction, the mechanical energy stays the same. At the endpoints, it's all spring potential. Going through equilibrium, it's all kinetic. Anywhere else, it's made up of kinetic plus spring potential. Maximum when it no, not maximum, it stays the same the whole time. 0, nope, it's not 0. When it reaches maximum displacement. C, that's when the kinetic energy is 0. That's not where the mechanical energy is 0. Remember, mechanical energy is made up of both kinetic plus spring potential. Nope, it's not 0 when it passes through equilibrium. That's where the spring potential energy is 0. Minimum when it passes through the equilibrium point. Nope. That's where actually the spring potential energy is 0, right? As you can see there from the picture. Okay, good. So you'll have to, explain it. This is non-zero constant. You can just say it's constant. It's made up of kinetic plus spring potential, or maybe write something like I've already written. Constant C above, something like that. Above by, meaning what I just wrote there. So this one, when you're actually doing the test, you could just type this out. This isn't so bad. Okay. So we have a cart attached to an ideal spring, force constant. There's a spring constant. Undergo simple harmonic motion. What's the period? Okay. So the whole point of simple harmonic motion is if they tell you it's simple harmonic motion, it's a mass on a spring. The period is 2 pi square root of m over k. Let's make sure that that's actually right, m over k. So m is the mass, k is the spring constant. So unit-wise, I would have kilograms divided by k, which is newtons per meter. So the meter would pop up here. I just want to make sure I have the formula right. So I'm looking at the units underneath the radical. And then a newton is a kilogram meter per second squared. And up here I've got a kilogram meter. So the kilogram meters cancel out. The second squared pops up to the numerator, and I've got the radical there. Okay, so the period should be in seconds, so that's good. So we actually have everything. They're asking for what's the period. Here's a formula that says the period is equal to, and we have everything. Mass is in kilograms, spring constant in newtons per meter, which we need. So the period will come out in seconds. So put the numbers in for that one. The only other thing to mention here is that the frequency is 1 over the period. So if I want to write it like this, I could do 1 over 2 pi square root of k over m. Okay? Again, the power of this, knowing it's simple harmonic motion, it becomes a pretty easy to work with formula, right? It's very specific too. It's a simple harmonic problem. This is what we have for simple harmonic motion. Okay, next one. As shown in the picture, a given force is applied to a rod at several places. In which case is the torque the greatest? Okay, so here's it's the same force applied at different places and different angles. 5 doesn't even make it rotate. This torque is 0. Same force here, but this, the number 2, is sort of towards the middle. I'm trying to see if anything is going to beat the first one. So in the first one, we have all of the force perpendicular all the way at the end. So in 3 and 4, the force is at some sort of angle. It's not perpendicular. It's not perpendicular in 3 and 4. So I would pick one. Torque is R perpendicular F. Choice 1 has largest R, and it's perpendicular, and F is perpendicular. So something like that. And again, you could write this on a piece of paper, take a picture of it, upload it, but probably this one you could almost just type it out too. Just say torque is R perpendicular. You could type out the word perpendicular times F, and choice 1 has the largest R, and F is perpendicular to R. So however you want to do that. By the way, during the test, I'll be available. You can send me any emails you want to during the test if you have questions, things like that. Number 7, the rotating systems shown in the figure differ only in two identical movable masses are positioned a distance r from the axis on the left. Okay, so look at this. These masses are all the way on the edge, or r over 2 in this picture. If you release the hanging masses simultaneously from rest, block on the left lands first, the block on the right lands first. They both land at the same time. So it turns out the block on the right is going to land first. So and my explanation would be in right picture, and again, when you're answering a similar one, you could just type this out, but I'm doing it in this form. The right picture has a smaller I, that's moment of inertia, because the masses are closer to the pivot point. Whoops. Pivot point. So it's easier to rotate. Pivot. Oh, that's supposed to be point. Okay. And it's easier to rotate, and rotates easier. I mean, you could even say, and therefore lands first, but that's sort of implied. Okay, so less mass towards, away from the center, the easier it is to rotate. We did that demo in class, actually. Okay. Okay, so we have a solid cylinder. The mass is given. Can rotate on a frictionless axle through the center. So the key here is they're telling us it's a uniform solid cylinder. So we know what the moment of inertia is, or we can calculate it anyway. So the moment of inertia, it's 1/2 mr squared. So don't be surprised to see a similar problem. If you can do this one, you'll be able to do the one in the actual test. So remember, the rotational world, it's just a little bit more work than the linear world. In the linear world, we would just be given the mass and be able to work with that. Here it's the mass and the shape, how big is the shape, and you can calculate the moment of inertia. So we could actually do that for this problem. We have 1/2 the mass, 10 kilograms, and then the size of the thing. Let me continue reading a little bit. A rope wrapped around the outer radius 1 meter. So you can see from the picture R1 is 1 meter. So that's the size of the whole thing. So 1 meter squared. Good, so this isn't too bad to calculate. 5 kilogram meters squared. That's the moment of inertia. 1/2 10 times 1 squared. We're given a couple of forces. F1 over here is 5 newtons. And the distance over to that point is 1 meter. A second rope, half as far away, so 0.5 meters, that's what R2 is, 0.5 meters, exerts a force of 6 newtons. Okay. Now we actually have more torque trying to make it rotate clockwise. Let me clean that up a little bit. That is 5 newtons, right? Because it's 5 newtons out here at 1 meter compared to 6 newtons with the perpendicular distance of only 0.5 meters. So really this problem should say what is the magnitude of the angular acceleration, because I can already tell it's going to come out to be negative. So let's see, torque. So the net torque is I times alpha. So what are the actual torques? Well, we have 6 newtons, that's the force, perpendicular distance of 0.5 meters, making it rotate counterclockwise, which is actually the positive direction, and then minus 5 newtons, and then the perpendicular distance to where that force is acting, 1 meter. So you see this is 3 newton meters minus 5 newton meters, so minus 2 newton meters is I times alpha. So this is a rotational version of Newton's second law. So then alpha is minus 2 newton meters divided by I, which we already found, 5 kilogram meters squared. So 0.4 radians per second squared. Technically, it's negative. They must mean what is the magnitude of the angular acceleration. Okay, so you'll definitely have one of these Newton's second law for rotation problems. By that I mean torque I alpha, and then you fill in the actual torques. Okay, and again, the rotational world is just a little more tricky. We had to actually calculate I. In the linear world, they would just give you the mass, F is equal to ma, that kind of thing, figure out A. Here in the rotational world, though, it's, again, a little more tricky. So I would give you the formula for I with the problem. So make sure that you are familiar with this kind of problem. Again, if you can do this one, you can do the one that's on the actual test. A child is riding a merry-go-round that is turning at 7.18 revolutions per minute. 7.18 revolutions per minute. Again, that's a perfectly good number. It's just not an SI number. It's not in SI units. And the child is standing 4.65 meters from the center. So I'll just put the child out here. And we want to know 4.65. We want to know how fast the child is moving. So what's the speed, in other words? Okay, so what is the 7.18? It's the frequency. It's just not in SI units. So we know 1 minute is 60 seconds. And then the minutes cancel out. So then you have an actual frequency in SI units. So I'll leave it to you to figure out what that is. And then the speed, the formula for the speed, it's 2 pi r. That's the distance that you go around divided by the period. Or if you want to do it in terms of the frequency, this would be 2 pi r times f. So the farther you are from the axis of rotation, the faster you're moving. Okay? In terms of angular frequency, or just frequency in this case, whether you're here halfway to the center or here all the way on the outside, you have the same frequency. You both go through the same amount of revolutions per second. So the frequency is going to be the same. The angular speed is also the same. So remember, angular speed, 2 pi f. You go through the same amount of radians per second whether you're closer, I'll just pick this point, or you're farther away. You have the same, that's supposed to be a b, you have the same angular velocity or same frequency, but the farther you are from the center, the faster you're moving, because if you go around once and you're at position B, you go a greater distance in the same amount of time as somebody at position A. Okay, so make sure that you take a look back at this sort of problem. And then I guess the only other thing to add to this formula, to this problem, is don't forget that the linear speed, I've talked a lot about it, is related to the angular velocity in this way. Okay, so you got v is equal to omega r, you got omega is 2 pi f, and then you have v is equal to 2 pi r over the period, or 2 pi r times f. So, you know, all these are good formulas. Make sure that you know them. You'll see a similar problem, but again, I'll give you some other, I'll probably give you the speed, and maybe then you have to find out the angular velocity, something like that. So you've got all these to work with your rotational problem. Okay, it's going on to number 10. And again, I think on the actual test, work it out on a piece of paper, take a picture of it, email it to yourself, download it, and then on your desktop or wherever, and then upload it back into the problem. You can try typing it out. This one actually might not be too bad to actually type out. However you can come up with. Okay, a string is 2 meters long. Okay, so that's the length of the string, the actual length, 2 meters long. Fixed at both ends and tightened to the wave speed. Okay, so the speed of the pulse, 2 meters per second. What is the frequency of the standing wave in the picture? Okay, so we know the speed and we know the length. We also know that the speed is the frequency times the wavelength. Okay, and we're trying to figure out the frequency. So they're asking for frequency. I'm thinking, what do I know with frequency in terms of speed? And I have this. So the frequency then is the speed divided by the wavelength. Okay, I know the speed. I have the length. I don't quite have the wavelength yet. Remember, the wavelength is 2L divided by the mode. How do you get the mode? How many antinodes do you have? 1, 2, 3, 4, 5, 6. Remember, the mode is how many antinodes. Antinodes are the high spots. You always have one less antinode than nodes. The nodes are the low spots. 1, 2, 3, 4, 5, 6, 7. Okay, but M here is the amount of antinodes, the high spots. 1, 2, 3, 4, 5, 6. So the wavelength here, it's 2L divided by the mode, and that's 6. So the wavelength is 2/3 meter. Okay, and then you have everything. The speed's given, so the speed is 10 meters per second, divided by the wavelength, which is 2/3 meters. This comes out in 1/seconds, so it looks like... Okay, so I see when I did this that the speed is not 10, it's 18. I had the line from the previous problem going through the number, so that should actually be 18 meters per second. And then when you do the problem, you get 27 1/seconds, and a 1/second is a hertz. So that's what the frequency turns out to be, 27 there. Okay, good. So you'll see something like this. Make sure when you see a picture, you can count. You can figure out the mode. Again, not mass, mode. From looking at the picture, count the high spots. That's the mode. Okay, good. That's from chapter 15/16. If a satellite moves with a constant speed in a perfectly circular orbit around the Earth, what is the direction of the acceleration of the satellite? So I didn't put anything with Newton's universal gravitational force law on the problem, but you will see a problem with something going in a circle. It doesn't really matter what it is. In this problem, it's a satellite going around the Earth. Even though the speed is constant, the acceleration is going to be towards the center. This is the radial acceleration. Okay, it's towards the center. You might say, well, the speed is constant, so there's no acceleration. The direction is changing. So direction change. Let me start over here. Direction is changing. Changes. So we have acceleration, and it's equal to v squared over r. So this is the way it's moving. This is the way that's the direction of the acceleration. Okay, so let's see, inward towards the Earth. Yep. Right, in this picture, that's the Earth at the center. Outward, no, it's definitely not outward. In the forward direction, so it's moving in forward. It's moving on its own forward. It just has momentum forward. It keeps changing direction because of the force towards the center. Definitely not backwards. And it's not zero because the direction is changing. Okay, so you always have to have an acceleration towards the center if you're going in a circle. Okay, last one. A car is moving at a steady speed of 10 meters per second. 10 meters per second. And and that's the speed. Encounters a highway bump, something like this. A circular cross-section radius of 30 meters. Okay. All right, good. The car maintains its speed over the bump. So here's the car. What is the normal force exerted by the seat on a 60 kilogram passenger? So here's the normal force. And then let me move this out of the way. That was the radius. I'll get rid of it here. Here's the weight. So you can see the circular path that we have here. I'm going to actually draw the normal force less just to really emphasize the fact that there has to be a net force towards the center when you're going in a circle. So the weight is bigger than the normal force. That gives you a net force towards the center. And we want to know how much is this normal force. Now if you're just sitting there not moving, the normal force is equal to the weight. Here, the weight has to be bigger than the normal force for there to be a net force towards the center. So F is equal to MA, special kind of A, towards the center. This goes back to chapter 6, and we have mv squared over r. Now what are the actual forces towards the center? Well, we got the weight, which is larger than the normal force. So then the normal force, solving for the normal force, is going to be equal to the weight minus mv squared over r. So if v is 0, you can see the normal force is just equal to the weight. Here, the normal force is going to be something less than the weight because you're subtracting something from the weight, right? This is when you feel lighter in your seat. It feels like you're coming out of your seat. So how do I know how to do this problem? Well, we're going in a circle. This is what we have for circular motion in terms of forces, right? And then you have to fill in whatever comes in the dotted area here, the actual forces. This is going over a bump. Make sure you know how to do the problem where you're going through a dip in the road. So what happens when you go through this situation and your car's there at the bottom? Okay, good. Set it up the same and it'll just be a different free body diagram. We actually did this problem in the homework. Or it might not have been the homework, it might have just been one we did in class. But we've gone over very similar problems. Actually, I think it was in the notes, come to think of it now. Okay, very good. So going through this, and I was going to give you 2 hours, but I think maybe I'm going to add another 15 minutes to that, maybe 2 hours and 15 minutes, because I know it's going to take a while to type this stuff out. So 2:15, that means you get an extra hour than what you usually have, and hopefully that'll be enough time. For 12 problems, that's like 5 minutes to take the picture and upload it per problem, if you actually do that for every single problem. And some of them you don't have to. You can explain it just by typing it out. Okay, very good. So I'll change it to 2 hours and 15 minutes. The test is available on Wednesday from 5 to 7, so make sure you get in there at 5. You have, actually from 5 to 7:15. I'll have to change that. You'll have that whole 2 hours and 15 minutes. Send me an email if you have any problems with it. I'll be standing by answering any emails that you might have. Okay? Any questions, make sure you email me as well, and we can talk about it then. You got about, 2 days to go until then. All right, talk to you soon.